Hey guys, welcome back to Rocket Gyan, my fellow space tubers, and today it's an exciting day indeed because we are sending something to the moon, and this is a thing which we are sending, and this thing or this satellite will help us understand the lunar orbit in a better way, and it will help us pave the way for the gateway and the Artemis program. So this is indeed very important mission for NASA and for Artemis and for us also, because it will help finally it will help humans to go back to the moon. So how are you all hi Skyprop, hi Andrew Crawl, hi Wildflower. Is it buffering? I don't think so. I hope now it's all right. It buffered a little, but I think now it's all right. So yes, yep. Right now, these are not the live views. So this is not the sunset which you will watch, because at the time of the launch it will be night in New Zealand. So there's that. And yes, welcome all. So let's just jump into it and understand what the hell we have for this mission. Okay, so first of all, the Electron space rocket will be used. So it's a very interesting mission in this scenario also, because a small sat launcher which barely can put a satellite into low Earth orbit is sending something to the moon. Isn't this fascinating? Like, the payload capacity for this low Earth orbit is just 300 kilograms, and it is putting something to the moon. Isn't it great? Because it is. And the Rocket Lab is not stopping there. They are planning for the Venus missions also and the Mars mission also. So we'll see those one by one, but this is an Electron spacecraft, again Electron rocket, and this is how it looks like. Just a second, I'll tell you. Yeah, there you go. So this is the rocket, which it has two stages, the first stage and the second stage, and then there will be a third stage also for today, and that I'll explain you in a bit. But right now this is a two-stage rocket. The first stage is powered by 7 Rutherford engines, and these Rutherford engines run on RP1 and LOX as its fuel, and runs on electric pump fed cycle. So that is unique for a rocket and makes much more sense for a small sat launcher. And the second stage is also a Rutherford engine, but it's a vacuum optimized engine. So and yes, it also runs on electric pump fed cycle. So there is a battery hot swap which you will see in the launch because of that. And then the payload, in the payload we'll have a CAPSTONE mission, but we'll also have the Photon spacecraft. And this Photon spacecraft is necessary, is the key basically for sending something to the deep space, the moon, Mars, or the Venus. So we'll see what how does it look like and how does it work. So right now in the payload bay you will see the Photon as well as the CAPSTONE. So there's that. I can move on to the next bit now. Okay, so there you go. The Photon spacecraft, you can say a flight proven. Yes, it has flown before. It uses Hypercurie engine which is used in the kick stages of Electron. So launch, satellite, ground services, and on orbit missions operations in a turnkey package. So you can say it's a reliable and affordable spacecraft and satellite solution to reach orbit faster, and that's what it is doing basically. So you can say Rocket Lab built satellites enable mission in low Earth orbit to planetary science and exploratory mission to the moon, Mars, Venus, and beyond. Yes, this is capable of doing that. So this is a small, basically this spacecraft is Photon spacecraft is nothing but a spacecraft or a propulsion system which has its own power, on communication, on propulsion, and on star tracking, basically navigation and everything. And it is responsible for sending the CAPSTONE mission to the journey to the moon. Electron will deploy the Photon spacecraft in a low Earth orbit because that is what it is capable of, and then the Photon spacecraft will do the series of burn, which I'll explain you, and then it will raise the apogee to reach to the moon. So yes, Wildflower, as you noted, it will be a slow mission. It won't be a fast mission. So there is that, and here you can see this is how it looks like for the Mars mission. It will be modified for this. Bigger antenna and solar panels would work. Would require for a Mars mission because it is going further away from the sun. This is a moon mission. This is how the Photon spacecraft looks like right now. This is for the moon mission. This is the CAPSTONE spacecraft, the satellite which is responsible for all the science, and then this is the Venus one. Okay, so yeah, this is how it looks like. So now let's move on and understand this CAPSTONE mission. So this CAPSTONE mission is nothing but it stands for, again I said, the NASA is very um creative in naming their mission. So this is a CAPSTONE mission stands for Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment. It is a lunar orbit that will test and verify the calculated orbital stability planned for Gateway Space Station. It's a 12U CubeSat, and it will also test a navigation system that will measure its position relative to the LRO, which is Lunar Reconnaissance Orbiter, which is in the orbit of Moon right now. So the main objective for this is that only, but right now the launch mass, many of you are wondering about its launch mass. So this is how it looks like. The launch mass is around 25 kilograms. That's it. 12U CubeSat, 25 kilogram, almost a microwave sized CubeSat, which you can see here. And it is going to a near rectilinear halo orbit, and in which the perigee altitude will be around 1500 kilometer and apogee will be way above, like 70,000 kilometers. So it will be a elliptical polar orbit around the moon. Okay, so there's that, and let me just tell you like the mission objectives and everything. So talking about the mission objectives, as I said, this is basically this spacecraft, if I tell you in the layman terms, this spacecraft is a pathfinder for the gateway. So it will test all the orbital parameters, like how much fuel is required for in orbit maneuvers, the orbital stability, and the navigation system. It will also navigation system with the LRO, because in future you don't want your navigation system to rely back on Earth. You want your satellites to be autonomous enough and determine its own position with the help of other satellites. So LRO will be doing its own job on the orbit of the moon, but with the help of LRO it will be able to determine its own position relative to the LRO. That is a navigation system which they'll try to figure it out. And yes, talking about the actual mission objective, so verify the characteristic of cislunar linear near rectilinear halo orbit, demonstrate entering and maintaining this unique orbit that provides a highly efficient path to the moon surface and back. And yes, this is a very stable orbit because it does not require much of fuel. This is a this orbit was found by NASA and it has been patented by NASA because it's such a good orbit to be in. But then also there is, like, at perigee, all the wonkiness happens because the lunar surface is very unregular. So because of that, the gravity changes and there is some issues with the orbit. So that is that is the thing which they want to test in orbit at perigee, how stable it will be, what will be the changes in the orbit. And the mission duration will be around 9 months for this one. And yes, this will also demonstrate the navigation services that will allow spacecraft to determine their location relative to the moon without relying exclusively on tracking from Earth. So there you go, the gateway program. It will basically help the gateway program to be in sight, and that will indirectly help the Artemis program. So now let's move on to one important video which you should see, and you will understand from this one like how the orbit is, what the spacecraft would be doing, and how it will be entering to the orbit and all those things. So let's just see this one. So this ballistic lunar transfer, okay, let's just see what it is. Here you can see the apogee raising. So this upper stage burn and apogee raising is done at the perigee, which is the most efficient way to burn. If you have played KSP and you have been using nuclear engines, you know what type of maneuver it is, because it is most efficient to burn at the perigee to any other point to extend the apogee, which means if you are giving speed at already high speed place, then the apogee will be easier to extend. So that's what it will do. It will have some certain orbits, like it will go like this and then it will again do the burn here, it will go like this, again do the burn. So it will do a series of maneuvers to raise the apogee, and it will not raise the apogee just to the moon. It will raise the apogee further to the moon, further off the moon. Just see this. There you go. At such a high apogee, the sun's gravity raises perigee and changes inclination for free. So as I said, it will be going to a polar orbit. So this is a very effective plan which they have got in place. They'll be doing the what should I say, the inclination change maneuver to reach to a polar orbit with the help of the sun. They are not wasting not a single drop of fuel in doing the inclination change, which is a very costly maneuver if it is done all together by the fuel. So this is a very interesting way it will be going to the moon, and that is the reason why it is raising its apogee further from the moon. You'll see the actual orbits. Here you can see the moon is here. It will actually most probably it will raise the apogee at as much as 3 times the distance between the earth and the moon. You can see here. And once it is here, it will still be in the earth system, but since it is very much farther away from the earth system, the sun gravity will take its place and do its job, change the orbit of the moon, the capstone, which you can see. It's a very unique trajectory which it takes. And then finally it will arrive to the moon, and then obviously it will do its job for the gateway program. There you go. This is the near rectilinear halo orbit, and I'll talk about the benefits of this one and why they have chosen this elliptical orbit and not a circular one. This is the navigation system. Yep, and there you go. I hope you got an idea of how the things would look like. So let's have a look at the orbit now. So as I said, it will go to a near rectilinear halo orbit. This is the Earth-centered initial frame, which means you'll look at the Earth and see the CAPSTONE mission going. So this is how it will look like around the moon. Okay, so this is how it will look like, and this is a moon standard, which means if you look at Earth Moon rotating frame, the Earth Moon rotating frame, and you will have the Earth and the moon in this frame, and this is how the orbit will look like. And here you can see the advantages of this orbit, because this orbit is so this orbit is actually, you can see in the Earth Moon reference rotating frame, the orbit is always facing the Earth. There is no communication blackout at all. So this is one reason why this orbit has been chosen, because there is no communication blackout from the Earth as well as from the moon, because it will be facing towards the South Pole. And if you can get like 3 satellites into the orbit, then you can triangulate your communication satellite to have the communication to the South Pole every time when it is in the orbit. So communication to the South Pole every time when it wants to communicate to the in the orbit. So yeah, there's that. And this is the moon centered initial frame, which means when the moon is centered and how it will look like. Just a second. There you go. So this is how it looks like. And talking about why it has been chosen, the reason why it has been chosen is specifically this elliptical orbit is because it's a very stable orbit. As I said, lunar orbit is not very stable because there are so much boulders from the in the moon that actually changes the gravity of the moon at certain points, and because of that the orbit degrades at some, after certain time. So you need to be having certain, a good amount of fuel to change the orbit and maintain its orbit. But at this specific orbit near rectilinear halo orbit, that is not the case, because at the perigee it is going very fast. So all those effects of the gravity is not seen by the spacecraft or the gateway for a very long time. So this is why it is able to remain stable for a very long time in that orbit without any use of fuel. So yeah, there you go. And this is the gateway. As I said, I won't talk about it much now. So let's just have a look at the mission itself. So this will be launching from the Electron rocket. The New Zealand will be the launch site. And yep, the launch window, you can see the June 28th to July 27th. So this is the launch window they'll have, and this is all those daily target T0 time. So they do have a long window, which is obviously the case with the lunar missions. And talking about the mission, we already have discussed about the mission objective. This is how the Photon spacecraft would look like. And here you can see now the talking about the mission profile. The mission profile is very much similar. Liftoff, stage 1 cutoff, stage 1 separation, stage 2 ignition, then the fairing separation, battery jettison, battery hot swap. Stage 2 will cut off, and then the photon will separate, and the photon will be responsible for actually sending it to the orbit of the moon. The Electron will put the photon and the capstone in a 165 kilometer low Earth orbit. So there is that. And yes, this is what I was talking about. So here you can see after liftoff, once the photon is separated at here, it will raise the apogee, which it will do in certain maneuvers. So it will raise the apogee, keep on raising the apogee till it will not directly go to the moon, as you just saw in the video. It will raise the apogee almost 3 times the distance between the earth and the moon, and then the sun will do its job to change the inclination of the orbit, and then it will arrive at the moon. So it is doing a very efficient orbital injection into the moon. So there's that, and it is very much necessary also, because electron does not have too much capability, and this is just a CubeSat also. So this CubeSat, and you can also see, like, after just 20 minutes of its final burn, the photon will separate the capstone. So after then it is all by itself. So if it has to do the those maneuvers in which it has to change the inclination of the orbit, that wouldn't have been possible from a CubeSat. So yeah, there is that. This is how the capstone looks like. And yeah, the launch vehicle is look like the first stage is there, the second stage, and as I said, the Photon spacecraft and the capstone spacecraft. So this is how it looks like. And this is the solar panels in it. You can see the solar panels here, the fuel tanks here, the hypercurie engine here. The dry mass is 55 kilograms and 25 kilograms is the capstone mass, and then obviously the wet mass will be there. So it will be around that maximum capability of the Electron rocket itself. So yeah, this is how all those things look like. So now let's see if we have can we see the launch from the America? Nope, you can't, because this is from the New Zealand. So there's that. And okay, I'll now switch over to the live stream. Let me just see if we have another live stream or a better one, because this is not the okay. Yep, And it is also at okay, wow, it is not a good one. Fine, no worries. Okay, there you go. This is the live views of the rocket, which you can see now.
Been readying the launch pad with vertical and avionics checks with the rocket, and have loaded Electron with its propellant types, kerosene and liquid oxygen. So right now, with just about 50 minutes left to lift off, all systems go for launch, and I'm going to hand it back over to you at Kennedy, Daryl.
All right, great report, Muriel. And quick question for you. Why launch from New Zealand?
Daryl, if you're looking for a launch site anywhere in the world, the ideal location is an island in the middle of the ocean, which New Zealand as a country makes a great option for. And if you're going to launch east, which you would like to do because you get that free push in the same rotation of the Earth, then the east coast of New Zealand is a great place to be, and Mahia on its peninsula jutting out over into the coast is a wonderful spot because we have very little air and marine traffic. So it's really a one in a million location.
It certainly is, and it's incredibly gorgeous, especially during the daytime, and hopefully in the future we can show you a daytime launch as well. Well, we've got a lot of cool stuff to show you coming up in our pre-launch show, as well as some great interviews. First, we'll take a closer look at the CAPSTONE mission itself, the very first spacecraft to fly as part of the Artemis program. Plus, we'll speak to an expert about this, the rectilinear halo orbit. What do we expect to learn, and how will we use the data? And from Capstone to Gateway, we'll talk to a NASA expert about the latest on plans for a lunar outpost where NASA astronauts will dock before going down to the surface of the moon. After liftoff, it will take about 4 months for Capstone to get into the near rectilinear halo orbit. Here's more on the orbit and the CubeSat 6-month pathfinder mission for the Lunar Gateway.
Before NASA's Artemis
Okay, so yeah, fog is you can kind of say, but New Zealand, it does not have much of a fog, so there you go.
Navigation experiment will test a unique lunar orbit that has never been flown before. This orbit will be home for NASA's Gateway, the future space outpost that will support visiting astronauts on their way to the moon and beyond. To help prepare for Gateway operations in this orbit, Capstone will fly the path first. The mission will be led by small business partner Advanced Space. Rocket Lab will launch the spacecraft. The gravities of Earth, the Sun, and the Moon will help propel it into deep space. As it nears its destination, Capstone will use its propulsion system to enter an elongated path around the Moon. The spacecraft will orbit between the gravities of Earth and the Moon in a precisely balanced dance. For 6 months, it will gather data about this crown-shaped trajectory known as a near-rectilinear halo orbit. The path provides an unobstructed view of Earth as it orbits the Moon's poles and allows for continuous communications with ground-based control centers. Capstone will also demonstrate a new onboard navigation system. It will communicate with NASA's moon-observing Lunar Reconnaissance Orbiter satellite to calculate its position. The technology could allow future spacecraft to pinpoint their location without having to entirely rely on tracking from Earth. Capstone's flight will demonstrate how this unique lunar orbit can support future spacecraft around the Moon, helping to launch a new era of human space exploration.
So this is already I have explained you, so you must have gotten it properly now.
Joining us now is Dr. Jeff Parker, the Chief Technology Officer with Advanced Space, the company operating this mission for NASA, and he brings Capstone, a literal life-size model of the exact
microwave
spacecraft.
sized.
What's great about this is you get perspective of how big this spacecraft is. It's this big.
That's right. This is a 12U form factor satellite. It's a full spacecraft in a small body. It's got a propulsion system down here. It's got an antenna that talks to the ground here. This is the antenna that talks to the Lunar Reconnaissance Orbiter, another satellite in orbit about the moon. Solar panels. These extend, so this isn't a fully unfurled solar panel, but yeah, that's right.
It's about right. The microwave oven was the analogy given, and it certainly looks like it's exactly that. Tell me, this is going into this near rectilinear halo orbit. How will it do that, and what's it going to do when it's there?
You bet. So the near rectilinear halo orbit is a challenging orbit to say, but it's a really impressive orbit for its operations. We use a low-energy transfer to get this guy into that orbit.
This very
and it uses
cool
very little
shots
fuel to get there.
the pad,
When
I
we
must
get
say.
there, this is a model of what the orbit looks like. Hopefully we can see that.
Yeah.
So Earth is in the middle, Moon goes around, and we form this crown shape about the Earth there. And then this orbit is just fantastic for what it needs to demonstrate. There we go. And it takes very little fuel to get into this orbit using this certain type of transfer to get there. And then it takes very little fuel to get down to the surface of the moon. We might even be able to use it to go out to asteroids. It's a gateway, and we're demonstrating this as the gateway for the Artemis program.
We're seeing a beautiful shot of Capstone right there on the top of the Electron rocket. You're with Advanced Space. We've got that team as well that's online tonight. They'll really start working when the mission fires up. What challenges do you expect to find once this gets into its orbit?
So nobody has ever flown one of these orbits before. Now, we have demonstrated this in simulation many times. We're ready for anything, even contingencies, but space flight is challenging. So we're ready for anything. We're going to go head on and teach NASA every lesson we learn.
And there's your team waving at us live from Colorado. That's the Advanced Space Headquarters in Colorado, where Capstone Mission Operations Center is located. A lively bunch tonight. Again, they're going to get working in 6 days.
That's right. That's right. I love this launch. It gives us 6 days to prepare between launch and the time that our team picks up the satellite on the way to the moon.
So tell me, what other lunar orbits were considered when you were first developing this? Because, you know, NASA gave you the funding for this mission and then said, hey, check it out for us.
Oh, sure. Yeah, we looked at a lot of different orbits like this, and they all had to have the same kind of requirements. So they all had to have a low fuel requirement to get this satellite, which only has so much fuel, into that orbit. Has to be a gateway, just like NASA's doing. And then NASA in general has tested out a lot of different orbits. We've landed on this NRHO because of its terrific viability.
And with this spacecraft here, when it maneuvers, it's these small little jets here at the bottom. Is that right?
Yep, that's right. Yeah, it has enough fuel to do everything we need. We have enough fuel for an extended mission as well. It's a monopropellant hydrazine system. Yeah, full spacecraft.
So, there you go.
And so in order for it to know
this-
where it is,
Okay.
you're telling me this antenna up here is what communicates with the LRO?
Yeah,
Another spacecraft.
That's right. Our spacecraft has two radios, one to talk to the Earth, which is a conventional approach, and one to talk to another spacecraft, the LRO. And this is a reverse radio for LRO, so it's perfect to talk to LRO. We're going to demonstrate navigation in a couple of ways. One with communications with LRO, which should be enough to navigate the spacecraft. Another one to do one-way communications with the DSN, which is a future advanced navigation technology. Everything we can do to try to help enable future lunar exploration. We envision a future that has a lot of missions in orbit about the moon. We're trying to help that out.
Absolutely. Thank you for bringing this. This is great, and for describing it, Jeff. But now we're going to go to the real capstone you see on your screen there and check back in with the launch team and our commentator, Muriel Baker. How are we looking so far, Muriel?
Thanks, Daryl. On your screen right now is the Range Control Center, located just a couple of kilometers back from the launch pad itself on the Mahia Peninsula. This peninsula is culturally
dropped her
significant
mic.
to local Māori people with ancestral ties to the land. So I want to acknowledge first the mana whenua, or the local people, for today's historic launch. Now, within range control, along the back row of the control center, starting from the right of your screen and moving left, sits two of our Photon engineers managing the spacecraft's tank and communications, and our IT support engineer. Across the aisle is our senior launch conductor supporting the flight director based out of Mission Control in Auckland. Next to them are 2 engineers responsible for the health of the Electron rocket's engines and its reaction control systems. Their call names are Prop and Stage. So in front of them sit the engineers looking after Electron's guidance, navigation and control, and monitoring the state of the rocket's flight computers and software. Along the front row sits our GCs, or ground control operators, who monitor the launch pad's ground systems. And to their left, on the right of your screen, closest to the camera, are the avionics operators with eyes on the operational status of the rocket's electrical systems. Behind them in the middle are the range and launch safety officers, keeping a close watch on the launch pad's surroundings. Now, cutting to mission control here on your screen, this hub is in Auckland, and it's home to our engineers and technicians whose focus is on our Photon and Lunar upper stage and the CAPSTONE mission beyond Earth orbit. In the front row, furthest from the camera starting from the right, we have engineering support for the flight software on the Photon Lunar upper stage. In the middle of the row to the end are the engineers managing ground tracking for today's launch. And then on the end is our operator with eyes on Photon's Hypercurie engine. Behind them, starting closest to the camera and moving right, we have the guidance, navigation and control engineers who are across Photon and CAPSTONE's path to the moon. Their call name is Fido. In the middle sits the spacecraft engineer supporting Photon's communication software, and on the end sits Space Ops software ensuring our telemetry makes it from the Photon spacecraft to the operator. Now moving to the back row, starting from the right, sits our weather officer for today's mission, followed by the engineer managing the IT systems, linking range and mission controls, and then our team lead, responsible for our hardware simulation platform called HITL, which we use to simulate multiple flights to orbit before each mission we launch. And next to them sits Tank, which monitors Photon's fluid systems to ensure its Hypercurie engine is provided with its propellants. And finally, at the end of the row is our Director of GNC, Dr. Jonathan Curry. So with that, we are now at T-minus 38 minutes and counting, and proceeding comfortably with the countdown to liftoff. A quick reminder that launch today is set for 9:55 p.m. New Zealand time, or 9:55 a.m. UTC. Over to you, Daryl.
All right, thank you, Muriel. And it'll be 5:55 a.m. Eastern time as well.
So this mission itself is a very important mission for Rocket Lab, because, as I said, this going to the moon and hitting the moon is actually done by the Photon spacecraft. So if they are able to do that, then obviously they have the capability to actually send something to the moon on their own, and that is a very cool thing to have, I must say that.
Of the missions that we're trying to develop, and small satellites actually gives us the benefit of doing, taking bigger risk. And so having the small satellites being able to, utilize and develop the technology for the bigger missions like the Gateway, is one of the reasons why we choose the CAPSTONE.
And so what are the most important factors when you go to design a small satellite?
But definitely, I think it's going to be understanding the mission architecture, where you're going, understanding the requirements, the environment, and trying to develop that technology so you can infuse it later into the bigger missions.
It's fascinating to hear about how NASA is working with small businesses and these small satellites to get big jobs done. What are the biggest technological advancements you've seen in small satellites?
I think the beauty for small satellites has been that not only are we able to develop the technology really fast and quickly, and mature it, but also being able to now do a pathfinder's missions like the CAPSTONE is going to be for the Gateway. And so that actually gives us a lot of benefits, because we can turn around and really develop and mature that technology.
Which will help the mission behind us right here, which is the SLS, not launching today, but a beautiful shot on the pad. We've got two different rockets on two different pads in vastly different locations. On a more personal note, Ali, I was reading an article about your personal journey here, and it begins with an 8.0 magnitude earthquake in Mexico City back in 1985. 5,000 people killed. Devastated Mexico City, where you were born and raised before you came here. Tell me a little about your personal journey and how that sparked you and your mother's journey here to the United States?
Well, definitely. I mean, it's a long story, but just to make it short, when the earthquake happened, my mother, had 4 children. I was the oldest one of 4, and she did not really had a well education. So for her to be able to survive, in Mexico at that time, it was not viable. So she decided to move to the United States and, move with her 4 children. And I was, the oldest one. So I moved with my mother here, and, I had to learn the culture, understand, learn the language too, right? And then be able to get adjusted to this new world. And, it took me some time, obviously, like anybody,
You went to school,
yes,
dropped out because of it, and then went back.
That's right. I decided to go back to school after many years because, I have 2 small children with mental illness. And for me, that was the drive to actually, get into school and get a degree, to be able to have them, have a better life. And for me, going back to school was the drive. And so I did it, and I graduated. And then when I was graduated, my professor actually told me there's an internship at NASA. I ended up, working at NASA, not thinking that was the path that I was going to take. But, I'm here, and I'm really happy to be here.
How about that? What an inspiring story, Ali. Thank you for sharing it with us, overcoming all those hardships to be here at NASA.
Thank you.
Good luck on the launch, and thank you again for being here. Well, we've showed you how CAPSTONE is a pathfinder mission for NASA's Lunar Gateway. As NASA astronaut Randy Bresnik will show you, the planned orbiting lunar outpost is the first step to fulfilling plans for a more permanent presence on the moon.
Home.
So guys, let's just understand this mission. You must have got all the idea that is indeed needed for this mission, to understand this mission. But let me just tell you that this near rectilinear halo orbit, as I said, is a very important orbit. It's so important in lunar exploration that NASA has patented it so that no one else can use it. So therefore, because this is such a good orbit, it requires minimal, literally no fuel, I can say minimal to no fuel, to maintain the orbit around the moon. And let me just tell you, to maintain the orbit around the moon is not a easy task. The uneven surface of the moon causes such a good amount of gravity change, which causes the orbit to degrade and finally crash into the lunar surface. So to have an orbit which does not get interfered by these external changes is a very, very, very good discovery. And this mission is bound to test that orbit only. This will be a 9-month mission in which it will test the characteristics of the orbit, see if how much fuel would be required to raise the orbit, and it will do all those things at the perigee. It will measure the changes at the perigee. It will if required, it will boost the orbit at the perigee. So most of the science with respect to the orbit will be done at the perigee itself. And then talking about the LRO, as you just saw that the LRO had that receiving antenna, right? And this CAPSTONE had that receiving antenna, and it is necessary because LRO is meant to send, it is not meant to receive as such, So that receiving antenna is there on CAPSTONE. It is therefore big because it has to catch the signals from LRO. So it will be able to detect its own position with the help of that, and because of that it will be able to maintain the orbit inclination, orbit change, whatever it is required, because it will be able to measure its own position where it is, and basically be autonomous in all those orbit boosting and orbit changing maneuvers. So it's a very, very critical thing to have.
It will lead the way for Gateway, a much larger lunar outpost where astronauts will go. What's the difference between getting CAPSTONE into that orbit versus the Lunar Gateway?
One of the really interesting things with the orbit mechanics is we can sort of play with, how much propellant it takes to get somewhere and the time it takes. So CAPSTONE is using a ballistic lunar transfer. So it'll take 3 months to get to NRHO, but it'll use a quarter of the delta velocity that we'll need when we fly this with Artemis and the crew. So the crew will only spend, 5 to 10 days in transit. We'll fly very close to the moon and use the moon to slingshot us out there, but it takes more delta velocity or, relative propellant amount. So, we can play with both the time and the duration to get into NRHO based on whether we're flying crew or you're doing something so uncrewed like the CAPSTONE mission.
And looking at this near rectilinear halo orbit, you can see it really goes quickly around the moon, but spends more time away from it. Why is that, and are there advantages or disadvantages to that?
Yeah, so the NRHO, or near rectilinear halo orbit, it's an elliptical orbit. So when you're close to the moon, the spacecraft, any spacecraft will fly very fast. You'll go over the north pole of the moon in about a day, but then we spend about 6 days over the big part below the south pole of the orbit. So you go very fast close to the moon, slow when you're away from the moon. But the reason we're in this orbit is it's incredibly stable, but also relatively close to the moon. So with that stability, we only need the equivalent of 10 meters per second of delta velocity for a whole year to maintain the orbit, which is very small in spacecraft terms. So that means we can put the gateway there for 10, 15 years and not need a lot of propellant to keep it there.
As I said.
But it's also close enough to the moon that the human landing system can access the South Pole. We can do the human exploration in the future, as well as have that stability for a good outpost capability. So really it was that balanced orbit for the long-term planning of Artemis and the objectives we need for human exploration.
Oh, that's very interesting. And so what is required in order to maintain that very unique orbit? Is it difficult?
So the orbit should be relatively easy to maintain, but that's why we want CAPSTONE to go first so we can collect all the data and validate the models. So it doesn't really matter what size the vehicles are, the orbit mechanics will work the same. So with CAPSTONE as the sort of pathfinder, it can demonstrate the navigation, the guidance, the propulsive capability to maintain the orbit, and we can really just extract from that the math to validate the orbits for Gateway, Orion, and Artemis missions. So the maintenance of the orbit is really fascinating, easy thing to do, so we can use these two missions to compare how they work. But the other advantages of this orbit is it's very stable for power and thermal and has continuous communication with Earth. So, the operations in this orbit are really good for that long-term deep space exploration capabilities that we want to demonstrate.
Najib Moranci, thank you so much for your time today.
Thank you for having me.
CAPSTONE packs a lot of technology into a very small package, and that's thanks to the engineers behind the spacecraft.
We're incredibly excited to be leading the CAPSTONE mission for NASA and demonstrating critical technologies that will not just help people return to the moon, will help people stay at the moon.
Before NASA sends their human-rated spacecraft, we want to send our CubeSat CAPSTONE to kind of work out the issues of how do you operate in this type of orbit? How do you do station keeping? How do you do navigation?
CAPSTONE is a pathfinder mission. CAPSTONE is going to be demonstrating how to put a space station at the moon.
So it's important for us to characterize that orbit and to understand what it is like to have spacecraft in that orbit.
The CAPSTONE mission is important because we'll be one of the first to explore the NRHO, the near rectilinear halo orbit, in and around Cislunar space, which will provide valuable experience and knowledge for NASA when they operate their Artemis missions.
What I think makes it a really interesting orbit is that it's kind of like balancing a pencil or a pin on the tip. Like, theoretically you can, but you never actually can.
At its core, CAPS is a peer-to-peer navigation system.
So CAPS is the Cislunar Autonomous Positioning System, and we'll be using that to sort of do autonomous lunar navigation in addition to demonstrating the near rectilinear halo orbit for NASA.
CAPS enables a future where many spacecraft can talk to each other, and they can help each other navigate, figure out where they are, avoid collisions, carry out their objectives, and so on.
Instead of talking to the ground, we can talk just directly with LRO and determine where we are in space, determine our position and our velocity in space.
You don't just know that you are, X kilometers separated. You can actually estimate the full six-dimensional state of both of those spacecraft. People have shown that mathematically for probably 15 years at this point, and this will be the first time that we actually get to demonstrate it in space.
Going to the moon is about learning. It's about learning how to operate in deep space without a lot of support from the ground.
I think it's very cool that we're working to put people back on the moon, especially because when I was growing up, that wasn't a big thing. It was a big thing we had done, but not a big thing that we were doing. And so I think it's really cool to be part of the generation that's kind of bringing that back.
Space travel is kind of like sea travel was many hundreds of years ago. It's hard, it's dangerous, but the resources out there, the knowledge out there will have tremendous impact on human life in the future.
It has been an exhilarating 2.5 years leading the development of the CAPSTONE mission for NASA. But what I'm most excited about is this is just the beginning of developing a foundation for the permanent return of humanity to the moon and a starting point for us to explore the rest of the solar system.
Well, you heard from the Advanced Space Engineers. Now you're seeing them live. This is an Advanced Space Headquarters in Colorado, where the CAPSTONE Mission Operations Control Center is. They will jump into action 6 days from today. That's when the spacecraft separates. The Advanced Space Team will then assess CAPSTONE's orbit, operate the payloads, and communicate with CAPSTONE through NASA's Deep Space Network and Terran Orbital. Back out to the pad, T-minus 24 minutes and counting. Here's a quick overview now of the launch preparations and what we can expect in the final minutes of countdown.
The countdown to launch is the most closely watched clock in mission control. Here are some of the things that take place at each milestone after the countdown begins. At T-minus 9 hours before launch, our crew are on site at Launch Complex 1 to configure the pad for launch and prepare to power on Electron for the day's operations. Meanwhile, our operators in mission control start checking in to their stations. At T-minus 7 hours, our operators will brief the launch director with a status update. Mission Control also receives its first weather check on what to expect at liftoff, including cloud cover and predicted wind speed at Launch Complex 1. Now, at T-minus 6 hours, our ground tracking stations begin to power up before Electron is prepared to go vertical on the pad. Soon afterward, Electron's Rutherford engines are tested with a short burst of engine fire to confirm all systems are operating as they should. At T-minus 5 hours through T-minus 3 hours, our range safety team runs through safety status checks for those on and around our launch complex on the peninsula, making sure the team and the public are kept safe during the day's launch attempt. Fuel loading of kerosene will soon begin on Electron, while additional vertical systems checks take place and the pad is evacuated. It's T-minus 3 hours now, and soon liquid oxygen will begin to flow into Electron. As the rocket slowly fills with this oxidizer, Electron's black body turns white as humidity in the air around the rocket freezes into a thin sheet of ice due to the freezing temperatures of the liquid oxygen inside. With 1 hour left to launch, it's crunch time for our operators. Vehicle cameras are switched to their launch settings. Our avionics team enables Electron for flight. Our final weather brief comes through, and the range safety status will confirm that the area is clear for launch. With 12 minutes left in the count, our launch director runs the go, no-go poll with our operators to make the final decision to proceed with the launch. All final checks are completed before we reach T-minus 2 minutes in the countdown. At this critical point, the countdown auto sequence begins and Electron's flight computers take over. The launch director begins counting down to liftoff from T-minus 10 seconds before the engines ignite 3 seconds before launch, and Electron lifts off the pad at T0 on its way to complete its next mission with the satellites on board.
Okay, it would be very interesting to see how this
And I was
pans
made
out
aware
today.
of one more small launch preparation, and that is eating the good luck peanuts. Dr. Jeffrey Parker is here. He's had his, and it's a tradition of navigators to do so before a big mission. Well, CAPSTONE is flying on a small rocket, but it has a long journey to get to the moon. A key technology that will get CAPSTONE there is the third stage of the Electron rocket called Photon. Let's head
You
back
know
down to New
about
Zealand
this
and join Muriel for
tradition
more.
of peanuts, guys? If anyone knows, please mention in the chat.
Thank you, Daryl. So to get the spacecraft out of low Earth orbit and on a ballistic lunar transfer to the moon, for the first time Rocket Lab is using its lunar configuration of our Photon spacecraft bus. Now, unlike the Apollo lunar missions of the 1960s and 70s, which took a free return trajectory to the moon, a fuel-efficient ballistic lunar transfer makes it possible to deploy CAPSTONE on a distant orbit using a small launch vehicle. The first 9 minutes or so of the mission will follow the typical mission profile of an Electron launch. The rocket will complete liftoff, first and second stage separation, and finally end with Photon separating from Electron's second stage in an elliptical orbit. Now that is where things start to get interesting, because once separated from Electron, Photon will carry out a series of orbit-raising maneuvers using its hypercurie engine, stretching its orbit into a prominent ellipse around Earth. About 6 days after launch, a final burn from the hypercurie engine will accelerate Photon to 24,500 miles per hour, enabling it to escape low Earth orbit and set CAPSTONE on a course for the moon. Within 20 minutes of the final burn, Photon will release CAPSTONE into space for the first leg of the CubeSat solo flight, and then CAPSTONE's journey to NRHO is expected to take around 4 months from that point. Now, once successfully inserted into the orbit, CAPSTONE is expected to remain there for at least 6 months, allowing NASA to study the orbit's dynamics. Now, here are two pivotal members of our Photon team to explain more about our Photon lunar upper stage.
My name is Ehsan Mosley. I'm the Chief Engineer for Space Systems at Rocket Lab.
I'm Rich Hunter, and I'm a Mission Design Engineer on the GNC team.
My job is to oversee the entire technical progress of the mission between conception to delivery of the 12U CubeSat to its end destination.
I do mission design and flight dynamics.
So talking about those peanuts, it's a tradition which was started during the Apollo time, because you know, it actually, when someone, I guess, I don't know exactly what happened at that point of time, but it started during that time. But the most extraordinary tradition is from Russia. Apparently, Yuri Gagarin on its first flight stopped the bus and peed on the right tire of the bus, and then went on to become the first man in the space. So, till now also, whenever Russian, astronauts or cosmonauts go out to space, they do this tradition of peeing onto the bus tire. This is something which, these superstitions, or you can say these things, are still believable in such a high scientific organization such as NASA or Roscosmos. And the reason is because you need that lady luck with you in space. And yes, this is a thing. You can be so sure about space. You can develop anything that you want. You must have read and researched everything that is related to your launch or to your mission. But you may miss one or two things, or you may just, if so happens that one thing had to be there, and by some maneuvers, it moved from that point to another, and then it caused the ship to explode. So some things are there, and in those scenarios, lady luck is required. So that is the reason why they are still going on with these traditions. So yes, it is very much interesting to see. Hey JJ, welcome to the stream.
Alignment. So then 2 of the alignment parameters are set within the first 20 minutes of the mission. So we need to set them really accurately so that they'll drift onto a moving target, to then hit a moving target, which is the moon, kind of 3 months later. When the mission ends for everybody else, I expect we'll be trying some zero pressure, deep space maneuvering to test our comm systems and our propulsion system and our Cislunar navigation for other missions like Venus.
I'm really proud of the technology we developed for this mission, but I'm most proud of the fact that this technology extends to future missions for Rocket Lab and NASA, such as our Mars Escapade mission.
There you go. Rocket Lab is not stopping there. T-minus 16 minutes and 40 seconds remaining. Things are
coming up
looking
soon
great.
on the go, no-go poll, one of the final gates we need to pass through for Electron and CAPSTONE to leave the pad for today's mission to the moon. Our talented and dedicated team have been making their way methodically through launch pad, range and vehicle preparations in the hours before liftoff. So to confirm we are proceeding all the way through to launch, let's listen in to mission control for that final go, no-go pull. That will be coming up in just a few moments, and we'll keep our fingers crossed for some very good news there.
Okay, so we are T-minus 16 minutes, almost under 16 minutes. Things are looking good. We can see the electron venting, and right now it is topping off all the liquid oxygen that is there, because obviously oxygen wants to remain in gaseous state, not in liquid state. So when it is in liquid state, it wants to become gas, and when it becomes gas, the pressure increases, and then those valves open up to release the pressure, because you don't want your rocket to explode because of excess pressure inside the tanks. So this is why those venting is there. And yes, this rocket is fully black. Those white thing which you are seeing is the moisture. The liquid oxygen is in cryogenic temperature minus 200 degrees C. So all those moisture at the launch site condenses and becomes ice at on the rocket, and gives such a beautiful color to this rocket. But let me just tell you that this
All
thing.
right, all stations LD on mission. Proceeding with the go no go poll at this time. Stage, you go.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC is go.
VMS.
VMS is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO. RSO is go. MET.
MET is go.
MM.
MM is go.
Tank.
Tank is go.
Prop Charlie.
Prop Charlie is go.
AV Charlie.
AV Charlie is go.
Ecom.
Ecom is go.
C2.
C2 is go.
Fighter.
Fighter is go.
LD sub.
LD sub is go.
There you go.
On all stations, that is the go-no-go sequence complete. We're currently T-minus 14 minutes, 8 seconds and counting. We go for terminal count start at T-minus 10 minutes. Be advised from this time the 3-word procedure is in effect.
3-word procedure is nothing but a hold, hold, hold. Anyone calls start,
And there we
the,
go.
the countdown is immediately halted no matter what the condition is.
Launch of the CAPSTONE mission to the moon. Our T0 launch time remains 9:55 p.m. New Zealand local time and 9:55 a.m. UTC, or 5:55 a.m. and 2:55 a.m. Eastern and Pacific. So let's go back to the Kennedy Space Center in Florida, where Daryl is with another special guest.
Thank you, Muriel. Got all the times covered. Appreciate that. Joining us now is Justin Treptow, Deputy of the Flight Opportunities and Small Spacecraft Technology Programs, to talk about how small businesses played a large role in this mission. Justin, great to have you back. You used to work here, spent 10 years here.
Yep.
You're now up at headquarters, but back in Florida for this launch.
Absolutely. I'm extraordinarily excited to be here for our lunar mission.
First question, why does NASA partner with small businesses like the ones that were involved in the CAPSTONE mission?
Well, it's an interesting interplay between government and commercial companies. With spacecraft getting smaller and more capable, we're seeing more entrants getting into the space industry. And as they get more and more experience on orbit, they're demonstrating real capabilities that NASA can partner with to lead missions like CAPSTONE.
And talking about this mission, the Rocket Lab was awarded around $13 million for this mission. So around that is actually a good amount for them, because the cost per launch is around $7 million. So double the amount they were getting, but obviously they were also supplying the Photon spacecraft too. So yes, that cost was valid. So yep, $13 million was awarded to them.
We wouldn't have the data for Gateway to take advantage of if Advanced Space wasn't here as a commercial partner on this project to bring the data from one project to another project.
That's fascinating. So you mentioned some of the benefits already that have been gained. And we've seen that through the development of CAPSTONE, right? Because NASA says, hey, go develop this. And then if there's spin-offs that are beneficial in other areas, you're starting to already see that with CAPSTONE?
Yeah, absolutely. Some of the examples, like one of the most obvious ones, is with the CAPSTONE propulsion system itself. Having a high delta V propulsion system on a CubeSat form factor is something that is, in the small sat world, kind of the holy grail. Being able to go somewhere and actually do something of value is really useful. And having Stellar Exploration develop a propulsion system that CAPSTONE's using to get into orbit around the moon in the NRHO and to stay there for an extended period of time is a propulsion system that's showing up in other commercial products that's infusing within the industry. So we're seeing the technology that NASA's funding for our missions go into other places within the space industry.
Already so quickly early on in this. That's impressive. We're now T-minus 10 minutes and counting until the liftoff of Rocket Lab's Electron rocket. I want to ask you about a previous Rocket Lab mission that NASA did. You're familiar with it, Alana 19, as part of the Venture Class Launch Services Initiative. What was the benefit of that, and what did we learn from that we're moving into this mission?
So the initial Alana 19 flight was a Venture Class Launch Service. Rocket Lab was a very new entry to the launch market at that point, and NASA wanted to get an opportunity to work with them on a project. And what we learned from that is that companies like Rocket Lab, like Tyvak, the bus supplier for this mission, they're very capable bringing their commercial best practices to the table and are able to really lead missions and projects. So it has, Alana 19 and the Venture Class Launch Service was like this first stepping stone to getting into these more advanced missions where our industry partners, again, are really taking a strong lead in the overall mission.
And briefly, Justin, give me a sneak peek at what's coming down the line. Any exciting partnerships with small businesses similar to this CAPSTONE mission?
Yep. So in the near future, we have a number of other CubeSats that are in the work. They're also going to be doing big technology demonstrations in small packages. We have Lunar Photon also going to the moon to shine a laser into the permanently shadowed craters of the moon to look for water. We have a Starling constellation of small spacecraft that's going to be doing on-orbit networking demonstrations and interfacing with other commercial partners on orbit, helping to alleviate conjunctions and to make space easier to access for all participants.
Justin Treptow, thank you very much, and welcome back.
Thank you very much, Joe.
A quick programming note before we go back down to New Zealand. I want to let you know that later this morning, Northrop Grumman's Cygnus spacecraft will be departing the International Space Station at 7:05 a.m. Eastern Time. We will have live coverage here on NASA TV starting at 6:45 a.m. Eastern Time. Again, Northrop Grumman's Cygnus spacecraft will be departing the International Space Station at 7:05 a.m. Eastern Time. All right, let's head back down to New Zealand. We are T-minus 8 minutes and counting, and Muriel Baker with the countdown.
Thank you, Daryl. It is T-minus 8 minutes and 10 seconds until liftoff. If you're just joining us, welcome to Rocket Lab's Mission Control Center in Auckland, New Zealand. Things are looking great so far for an on-time launch today from our private orbital range, Rocket Lab Launch Complex 1 on New Zealand's eastern shore. Now, you have seen the launch range and inside our mission and control centers. Now it is time to get you acquainted with the Electron rocket lifting off the pad today. And as you will have seen earlier in the show, we are taking an unconventional path to the moon, and that is because Electron is an unconventional rocket, the first of its kind in many ways, and one of the smallest orbital rockets in history to attempt to launch a spacecraft to lunar orbit. So here's a little bit more on Electron.
Okay, so
A small
T-minus
launcher
7 minutes until the liftoff.
Electron was the first of its kind to reach orbit when it first took to the skies in 2017, opening up access to space for small satellite operators. Today, it is the second most frequently launched U.S. rocket annually. More than 140 satellites have found their home in space across more than 24 Electron missions launched from Rocket Lab Launch Complex 1, the world's first and only private orbital spaceport. Designed, manufactured, and launched by Rocket Lab, Electron is a two-stage launch vehicle powered by liquid oxygen and rocket-grade kerosene. Much of its structures are made of advanced carbon composite material, including its propellant tanks, which is what gives Electron its sleek black look. The rocket is powered by 10 Rutherford engines, 9 at the bottom of the first stage, and a 10th space-optimized engine to power the second stage to orbit. The Rutherford engine is the world's first to use an electric pump feed cycle for orbital space travel, making use of electric motors and batteries to drive its propellant pumps. It's also 3D printed using additive manufacturing processes. Electron is also equipped with a third upper stage that serves as in-space propulsion to deploy payloads to orbit. In its most advanced form, this stage is called Photon, a spacecraft bus to support small satellite missions even beyond Earth orbit. It's to this structure that the CAPSTONE satellite is attached, ready to be carried on its way to its lunar destination in near rectilinear halo orbit.
So Shashikiran, talking about your question, why New Zealand and not launch from 39B? So first of all, this New Zealand is there because Electron is launching from there. Electron has a spaceport from the New Zealand. They launch from New Zealand, and that's why it is launching. And one more thing is that this is a CubeSat. So you know, ride sharing, getting a ride to the moon for a CubeSat is very, very difficult. So you need some dedicated launcher to do that job. And since it is a very small satellite, there is no as such launcher which would you know, provide the proper services. So therefore the Electron was chosen because it was apt for the service, it is reliable, and it can do the job. And since it launched from the New Zealand, so that's why it is launching from the New Zealand.
CAPSTONE payload into an initial low Earth orbit of just 165 kilometers. Now, from this initial parking orbit,
hey Glenn, how are you?
Hypercurie engine will perform a series of orbit raising maneuvers over 5 days to stretch its orbit into a prominent ellipse around Earth. Now, 6 days after launch, Hypercurie will ignite one final time, accelerating Photon to allow it to escape low Earth orbit and set CAPSTONE on a course for the moon. From there, CAPSTONE's journey to NRHO is expected to take around 4 months, with the CubeSat's team at Advanced Space's Mission Operations Center commanding the spacecraft to fire its thrusters to adjust its course accordingly. Now, if we are looking back at the pad camera now, we can see that the rocket's strong back has retracted and has moved into the launch position. This launch platform structure is what holds the umbilical lines, providing power to the rocket, which will fall away as Electron lifts off the pad. You can see Electron's icy white stripes on the outside of the rocket there too. Those are because of the super cold liquid oxygen propellant on the inside of the rocket, which freezes water on the outside, causing it to form those distinctive icy areas along the rocket's black carbon composite body. Now, our last weather update also confirmed that the wind speed at T0 is expected to be good for launch, further minimizing the weather risk to today's mission. Now, as we get closer to the countdown, it is worth pointing out what kind of views to expect from launch today. As always, we'll be bringing you the live views you see on your screen from various cameras at the pad and at range control. However, for this mission, we won't have the typical onboard vehicle cameras you might be familiar with for Electron launches, and that is because this mission has extensive telemetry requirements. So to reduce the load on systems and operators, we've streamlined the mission down to essential systems only. Now, while we won't have those live vehicle feeds to show you, we will be broadcasting mission data and animations, so you can keep up with the launch progress throughout the ascent. And now we are coming up to a critical juncture in the lead up to launch, the switch to the countdown auto sequence. The team are tracking no issues with the launch vehicle. CAPSTONE and Photon remain healthy, and the weather is looking good. So at T-minus 2 minutes, very shortly, that autonomous flight computer on Electron will take over the launch countdown, followed by the call that LOX loading is complete on Electron. Then at T-minus 1 minute, we can expect confirmation that the vehicle's first and second stages are pressurized for launch. So, followed by that will be the iconic final countdown to liftoff at T-minus 10 seconds and engine ignition at T-minus 3 seconds. We'll hand over now to Mission Control and listen into those calls to launch.
Launch vehicle is fully on.
We are team under 2 minutes now, and it's looking great. It's looking very great right now, and it's finally happening. Rocket Lab is launching its first mission to the moon, and if successful, that will open more gateways to, you know, launch to the Venus, launch to the Mars, and whatnot. Well, I didn't expect Rocket Lab's Electron to be so capable that it will be able to, launch something to the moon. So, yeah, there's that. Wow. So T minus 1 minute and 10 seconds remaining. You can see the venting is not so much right now because
all helium anti-gathering disabled.
The valves are closed to maintain the tank pressure. Topping off is completed. T minus 1 minute. Yeah, this is happening. This is happening. Okay. Rocket Lab's first mission to the moon, and in fact it would be first mission to the moon from the New Zealand too.
High flow engine purge enabled.
T minus 30 seconds remaining.
What a deluge activated.
T minus 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10.
10, 9, 8, 7, 6, 5, 4, 3, 2.
Ignition. Liftoff. Whoa. Dude. Just look at that go. Wow.
HVB discharge now.
That is something indeed. That is so beautiful right now. Wow. Okay. Mission to the moon. Here we go. Finally something going to the moon after so long.
Entering burnout detect mode.
Sun in the night sky. So now the next event coming up is the Max Q. Max Q is responsible for, it's the highest pressure which the rocket experiences, and if it is able to surpass that, that means the structural integrity of the rocket is good.
And Electron is in the air and onward to the moon for the CAPSTONE mission. That rocket is soaring through this nighttime sky, now past 14 kilometers in altitude in these past few moments. Now, things look to be continuing nominally, which means that shortly, Electron will come up against max Q, or maximum dynamic pressure. Now, this is the moment when Electron will experience its most amount of mechanical stress as it travels through the atmosphere. And I can confirm from mission control that we have had max Q confirmed, so that was a successful pass through that milestone, and Electron is onward to low Earth orbit. So propulsion appears nominal on that first stage, and the Photon Lunar upper stage and CAPSTONE spacecraft remain healthy inside the rocket's fairing. We are coming up soon on 3 events in the launch timeline that will occur in very short succession. So soon, the 9 Rutherford engines powering Electron right now will diminish their power and then shut off completely. That command is signaled by the rocket's flight computer and then called across mission control comms as MECO, or main engine cutoff. Now, once that action is complete, Electron will separate its first and second stages. The main booster will continue to slow and remain behind while the second stage carries on with the mission with the ignition of its single Rutherford engine.
There you go, staging
and
has...
we have had MECO confirmed.
There you go.
On the fairing separation for the mission. So just to confirm from mission control comms, we have had MECO
Best animation
and second
yet.
stage separation, and it's carrying on now, as you can see in that
HVB
animation.
discharge nominal.
So soon we will be coming up to the fairing separation of this mission. That is the jettison of the fairing halves, or the rocket's nose cone that sits on top of the second stage. So now that Electron is well past the Kármán line, we don't need that fairing. It served its purpose to protect the payload and the Photon upper stage during the launch through Earth's atmosphere. So again, that fairing will separate shortly in preparation for the final stage separation between
There
the
you
second
go,
stage
fairing
and Photon.
separated. Stage to...
So there we go, we heard it on comms. We have had fairing separation on that second stage, and so there's confirmation that mission is
Now
continuing
the
as it should,
fuel
with
is
CAPSTONE
dropping.
and the Photon Lunar upper stage now exposed to space and no longer needing that protection through Earth's atmosphere. Now, it's very exciting to see this mission up and in the air. And if you have just joined us, we have had a great start to today's journey to the moon. We have successfully cleared the pad at Launch Complex 1 just a few moments ago, and we are now well on our way to space, having completed that first successful pass through max Q, main engine cutoff, stage separation, and fairing jettison to reach this point now in the mission. Now, Electron's second stage remains attached to the Photon Lunar upper stage carrying CAPSTONE, providing it with that assist to the mission's parking orbit at 165 kilometers above Earth. The rocket's second stage is moving along nicely on its continued ascent, now traveling at a very fast speed of more than 9,000 kilometers an hour. Soon, the second stage on the Electron rocket, which is powered by our vacuum-optimized Rutherford engine, soon the batteries on that engine will need to be swapped out. Now, this is a unique aspect of our 3D printed engines because it's not many engines that are powered by batteries in the first place. In fact, the Rutherford became the first rocket engine in the world to reach space using an electric pump bead cycle when it was first launched.
So yes, this will use this will take around 3 to 4 months to reach the moon, and yep, the booster is not reusable. I'll answer your questions after this launch.
Running. We call that a battery hot swap, and that moment is coming up shortly. We will hopefully hear that on mission control comms.
Rocket Lab, yes, indeed, Pratim. Rocket Lab is killing it with not having the onboard cameras. This is looking very, very cool, and those trajectory and those fuel gauges are just the cherry on the top. So we are T plus 5 minutes from the launch. You can see
starting to throttle down.
175 kilometer is achieved. 12,000 kilometer per hour is the velocity. Everything is looking great.
Stage 2 guidance remains nominal, 200 seconds remaining.
Now the next step is the battery hot swap, which
if we
means...
take a look at the graphics on the right-hand side of our screen, we can see the measurements for the propellant on Electron. So on your left, you have the kerosene propellant and the level of the tanks that it is now at. So we're at 45% and counting, sitting at a nice and warm 8 degrees in temperature. And that is very warm compared to the liquid oxygen temperature, our other propellant. So that is sitting at a nice and chilly minus 178 degrees with 40% or so propellant left.
Yep, you can see those temperature differences. Temperature difference of fuel is just inside one rocket, isn't it?
And
cool?
There we have the call that battery hot swap on the second stage was successful. Now, next we should expect to hear one of our operators in mission control call out that Electron is orbital, indicating that the rocket is in the right place ahead of stage separation. So SECO, the acronym for Second Engine Cutoff, and the subsequent stage separation follow relatively the same procedure as Main Engine Cutoff, where the Rutherford engine on the second stage will shut off ahead of the final separation of the vehicle between the second stage and the Photon Lunar upper stage. There will be a bit of a gap between that final separation and the first hypercurie burn, as this stage separation places the Photon Lunar upper stage in an elliptical orbit of Earth first. Now, a reminder that 165 low Earth orbit is just the first orbital phase for this CAPSTONE mission, with Photon and CAPSTONE's orbit continuously raised higher and higher over the next few days, with a series of engine burns on the upper stage. I'll go into more detail about Photon's phasing orbits and CAPSTONE's path to the moon shortly, once Electron has completed SECO and stage separation. Let's listen into mission control comms.
Okay, T plus 7 minutes, only 17% of fuel left. Almost 20,000 kilometer per hour velocity is achieved. We are coming in for the SECO, and in SECO it won't be pushing it towards the moon. It will be parking it towards in the low Earth orbit itself. So around 165 kilometer will be the orbit of the low Earth of the Earth, and then from there the Photon spacecraft, which is on the rocket right now, will have its own propulsion system, and that Photon spacecraft will be responsible for sending it to the moon.
Entering burnout detect mode.
and not only to the moon, even beyond the moon, because actually it will be sending it beyond the moon, almost 3 times the distance between the
So
Earth
quick
and the
check
moon.
on the speed and altitude of this
Guidance is
mission. We
internal,
are
25
traveling at more
seconds
than
remaining.
23,000 kilometers an hour. And while on the right you can see the altitude is at 175 kilometers, what goes up must come down, and we will lower ourselves into that 165 kilometer parking orbit very soon.
Cool. So talking about the communication delay from the Earth to the moon, so it's around 3 seconds only. The moon is relatively very close, and there you go. The SECO is completed.
SECO confirmed.
Photon is separated. To the moon. Guys, to the moon. Wow.
So with the Rutherford engine cooling down, that tells us that second engine cutoff was successful on Electron's second stage. And the Photon lunar upper stage has now departed into its low Earth orbit with the moon-bound CAPSTONE spacecraft on board. Now, as a reminder from here, Photon is in charge of the mission. With its relightable Hypercurie engine, Photon will begin maneuvering into a parking orbit just above substantial atmospheric drag, but below the Van Allen radiation belts. It is the perfect, stable platform from which to prepare for lunar departure. Now, once Photon is in the correct orbital alignment, the Hypercurie engine will ignite again, performing a burn to lift the highest point of Photon's orbit, the apogee. Now, as it gains altitude and also loses velocity, and so what goes up comes back down as Earth's gravity pulls it back towards the planet. When it reaches the lowest point, or perigee, once again Photon's Hypercurie engine ignites to increase velocity and raise its apogee higher. So if you've ever been on a swing set, swung to the top, came back down, and then kicked your legs out to throw your weight forward to reach even higher on the next swing, then you've followed similar principles to what our Photon upper stage will be doing in space. Now, as these phasing orbits get bigger, they take longer to complete. The first will only take around 90 minutes, while the last one will take around 15 hours. Then on the final phasing pass, Photon will ignite Hypercurie for a precision translunar injection burn, accelerating the upper stage and CAPSTONE to a top speed of nearly 11 kilometers per second, fast enough to break free of low Earth orbit on its way to the moon. The speed Photon is traveling at this point will shoot it well past the moon's orbit and to the edge of the Earth-Moon system on a transfer orbit. Lined up with the sun and using its gravitational pull to shape Photon's orbit to match speed with the moon, CAPSTONE will then be deployed and carry on the mission solo. And so with those first few Hypercurie burns scheduled in the coming hours, I'm going to send it back to Daryl and the team at the Kennedy Space Center. Daryl, I know you weren't here in person, but how was that for you guys over at KSC? My heart is still pounding. I know our team is thrilled at the successful first phase of this mission.
Oh, absolutely, Muriel. Wish I could have been there to watch it with you. And boy, what a beautiful picture from here. And congratulations so far on the success of the launch. Obviously, a lot more steps to go before CAPSTONE gets into its orbit, but looking good so far with a great beginning. Quick note on this rocket right behind me, the Space Launch System, NASA's Mega Moon rocket. It completed its wet dress rehearsal. It will be returning to the vehicle assembly building in just a matter of days. It's going back on Friday. Repaired to the hydrogen leak will be made, and then the next time it rolls back out to the pad right there, it will be ready to go to the moon. And what a beautiful shot that we see there. We are at daybreak here on the east coast of Florida. 5:59 is when first light arrived, and we've got some beautiful pictures there of our moon rocket. And now let's go back down to New Zealand, and joining us now is Bradley Smith, the Director of Launch Services at NASA's Kennedy Space Center. He's with the launch team in New Zealand. And I want to ask you, Bradley, first of all, you're a half world away, and there's a little bit of a small delay between us, but I want to ask you, how did the launch go from your perspective?
Oh, I am definitely half a world away. I landed in Auckland, and my first foray into New Zealand soil was a lost bag, so I had to go buy a new suit as soon as I landed. But yeah, I mean, the launch was absolutely fantastic. I mean, this has been for me gosh, 8 years in the making. You know, all the way back to 2014 when we put our trust in Rocket Lab with our initial VCLS Demo 1 award, contract award, right? And here we are, you know, that was a payload to go launch university CubeSats. And now here we are, not even a decade later, and this incredible team has just sent CAPSTONE on a ballistic trajectory to the lunar orbit, right? I mean, it's amazing how far Pete Beck and his company have come in the last 10 years, and we couldn't be prouder.
And you've been there on the journey most recently. Did you ever imagine, got to ask you, did you ever imagine that you would launch a mission to the moon on a 59-foot tall rocket?
I did not. And for on the order of $30 million, right? Between the payload and the launch service itself. It just goes to show the direction that NASA's going, right? Embracing this truly commercial approach to enable science and discovery for the agency.
So what's next for launch services?
Yeah, so for LSP, we've got, well, you know, it's as soon as I say we have a certain number of launches, those launches will immediately slip to the right? So we have somewhere in between 3 to 5 launches coming up. We have 2 more Venture class launch service class launches, both with providers that NASA has not flown with before. One with Relativity and also one with Firefly. Those will one launch from the Cape and one launch from Vandenberg Air Force Base. And then we have 2 end-to-end missions coming up as well from the West Coast. One is the JPSS-2 mission for our NOAA partners, Polar Earth Observation Satellite. And then we also have SWOT, which is a oceanography payload that's done jointly with CNES. So that's what's next for LSP programmatically. Of course, we continue to support our sister programs, Commercial Crew and Commercial Cargo, doing the launch vehicle work for those payloads as well.
Looking forward to those. Yeah, absolutely. Looking forward to those missions, Bradley. And thank you for your time. And sorry about the rough start in New Zealand, but the new suit looks good on you. But that launch looks even better.
Absolutely. I appreciate it.
All right. Thank you, Bradley. And that concludes our live coverage of the launch of CAPSTONE spacecraft. Over the next 6 days, Photon's engines will periodically ignite, and they will basically accelerate CAPSTONE beyond low Earth orbit and send it on a ballistic lunar transfer trajectory to the moon. If you'd like updates on its progress and how it's performing, there are 2 ways you can do it. You can follow us on Twitter. We're going to pull up a graphic here, @NASA Technology, or you can click on a QR code that we have. We're going to pop that up on the screen. There it is. That will take you to our CAPSTONE blog, where you can also find NASA's Eyes on the Solar System. This is an interactive real-time 3D data visualization where you can virtually ride along with the CubeSat. Pretty cool. We'll have that ready in about a week. And while you're capturing that QR code, I want to do one thing. I want to boop this rocket. Boop. Always wanted to do that. A special thank you to all of our guests on the show, as well as NASA's Space Technology Mission Directorate. Also to
Good morning,
Rocket Lab
everyone
for
in
partnering with us
US
on
right
this launch
now.
broadcast. I'm Daryl
Wow.
Mayo signing off from the Kennedy Space Center with the Space Launch System behind me at daybreak. For Rocket Lab's Muriel Baker and everyone here at NASA, thank you for watching. We leave you now with a replay of the CAPSTONE launch from New Zealand and remind you to keep looking up.
That was indeed
10,
a special launch.
9, 8, 7, 6, 5, 4, 3, 2, 1. Confirm liftoff.
HVB discharge now.
All right. and the moon rocket. This rocket looks so beautiful, I must say that, no matter how much it cost, but it looks so beautiful. Yeah, there's that. So finally, this thing which you are seeing in front of you is there in space, and the rocket's job is completed. Now the job is handed over to this spacecraft, the Photon and the Capstone. But right now the Capstone is still in its passenger seat, and now a Photon will be doing all of its work, because Capstone has to be there in lunar orbit for like 9 months, so he has a lot of work to do. So yeah, why not give some time more to be rested and getting ready to go. So yeah, that is pretty much about it. So talking about, we already talked about this Photon rocket. This is how the Capstone satellite looks like. It's a normal CubeSat size of a microwave, weighs around 25 kilograms, and yeah, this is how it looks like. So there you go. It will go to a near rectilinear halo Earth orbit, which you can see in front of you. This is from the Earth Moon rotating frame, and from here you can see the Earth is always in view of this satellite, so therefore there is no loss of communication at all. And in terms of the moon, you can see the perigee is at the north pole, and the apogee, which means the highest point of the orbit, is at the south pole, which makes this orbit very interesting, because it has more time in the south pole. Around 6 days it will be sending near the south pole, because of its apogee. It has to go such a long distance, and then come back down, and a very short duration time on the north pole. So it becomes very ideal for animation which are on the south pole. So yeah, this is a good um, orbit. So yes, let's just see if we have any other updates. But right now everything went as per the plan. So hey, yep, perfect Electron launch. There you go, the perfect one. And let me see if we have any questions, and we'll see if we have. And guys, if you haven't liked it already, please do leave a like below, because it really helps this channel. And please haven't already, because there are quite a lot of missions coming up, launches coming up on 30th of June. So around 4 live streams will be there. So do subscribe to this channel so that you don't miss any of them. And yes, let me see if we had any other questions. So is this booster recoverable? Nope, this is not. This is Electron. Yes, this is Electron rocket has its recovery program, but this one, in this mission, they did not do that. So they are still, that recovery program of Electron is still in the testing phase. So we'll see once that testing phase is properly completed and done, then they will move on to the recovery of each and every rocket. So yes, the mission phase lasts 6 months. Yes, 6 months is the mission phase. 9 months is, you can say, the total mission duration, because it will take 3 months around to get to the moon. So yep, the Oberth effect, that effect which comes into play when you are at perigee and you boost at that point of time and raise your apogee, which is the most efficient one, that is known as the Oberth effect. So yes, Pratim, you are right about that. Okay, so just subscribe to this channel, Shashikiran. You will be prepared next time, so you don't worry. You don't have to be prepared, actually. In this channel, that is the specialty of this channel. You don't have to be prepared anyway. Audience of this channel are from the the very general, or people who does not know anything about rockets, and are very technical people also. So I make sure I do justice for all of them. So I make my live streams and informations according to that. So yes, awesome launch. Thank you, JJ. Yep, that's a bot. There is something going on in YouTube recently. I have noticed that there's a lot of bots that have been surrounding this live stream community. I have seen those bots in the comment section, but not so much in these one. But okay, I guess it is. So no worries. Thank you so much for joining in. And if you want to support me, guys, if you like my work, please, please, please do support me by becoming a member or a Patreon. Link is down in the description. And I'll see you next time on 30th of June, most probably with 4 launches. So it will be a marathon for me. Literally, I won't be sleeping at that night. I have a 2 a.m. launch, 6 a.m. launch, 10 a.m. launch, 2 p.m. launch around that point of time. So there is no time to sleep at all. I don't know how I'll be. I guess I just have to drink a lot of coffee. So let's see how will that day go. So yeah, thank you so much for joining in. And until then, this is Pransh Royla. You just saw Rocket Gyan. Stay safe, stay healthy, and